Hey there, here I'm explaining how to implement a synchronous up-down counter using JK flip-flop. A counter, as the name suggests, is simply a device that can count. How we count in binary. Let me set it to up counting. So here we are counting from 0 to 7 in binary. And you can see that the green bit or the least significant bit changes every single time. And uh, again, the blue bit. When you see the blue bit, it flips every time the green bit is already 1. For example, here you can see the green bit is 1, then the blue bit changes to 1. The green bit is 1, the blue bit changes to 0. The green bit is 1, the bit changes to 1. Uh, it's like a tongue twister. So, anyway, then we have the red bit. Now, by observing, you can already guess when the red bit flips. Yes, it flips whenever both the blue bit and the green bit are already 1. So you can see here, when both the blue and green turns 1, the red bit flips. Again, when both of them becomes 1, the red bit flips. So this is one pattern that you have to observe. And we can observe a similar pattern for down counting. Let's switch it out. Even in down counting, you will observe that the green bit flips every time. And as for the blue bit flips whenever the green bit is 0. Unlike in the case of up counting, where the blue bit flipped whenever the green bit was 1. So you can see here, whenever the green bit is 0, the blue bit flips. Whenever the green bit is 0, the damn. Whenever the green bit is 0, the blue bit flips. And as for the red bit flips when both the blue and green are 0. So having this basic introduction about binary counting, we can proceed to understanding and implementing counters. Coming up next, we have the JK flip-flop. Let's try to understand the part we require to proceed. Let's quickly glance through the working of a JK flip-flop. Let me enable the flip-flop here and connect the heart or the clock to the flip-flop, and I have enabled the ticks already. So here in the truth table, you can see that when the combination JK is 0, there is no change in the state of Q. That is, for example, if I set Q to 1 by connecting like this, okay, that causes an error. Or let me just change it by making J1 and K0. And let me turn it back to 0, 0. Now you can see that it preserves the state of Q. And like all these changes happen on the whenever the clock turns on. For example, here you can see that when I make it 0, 1, the clock turns off. The moment the clock turns on, you see that this state has been updated. And the most interesting state, 1, 1, alternates the value of Q at every rising edge of the clock. So this is what we would be using majorly, this 1, 1 state. And also the 0, 0 state, which is used to preserve the value of Q. So we either use the no change state or the toggle state. So let's start making the counter. Or let me bring in the JK flip-flop here. And let me also bring in the pre-required connections. So here we see that we have preset, reset, and enable. Um, it is already mentioned what enable does. Preset is like used to set the value of the flip flop to 1, ignoring the clock cycle, and reset again overrides everything else and sets the value of the flip flop to 0 when activated. So here we can see when I'm turning on preset, the value of the flip flop turns to 1, and when I click on reset, the value of the flip flop turns to 0. So these are basically used to predetermine the state of the flip flop. We won't be needing these, so let's move on. So now we know that the least significant bit changes for every clock cycle. Let me first bring in the clock here. Let me put it a little far away because we would be needing the second and the third bits. So let me bring in the clock from here. Oh god, yeah, and enable the text. Okay, perfect. Now we also know that the flip-flop toggles between state when the value of jk is equal to 1. So we set both the value of j and k equal to 1, and this will be our least significant bit. For the second bit, we will again use another jk flip-flop. I'm copy pasting it, and the condition we noted earlier is that before that, let me just connect the default values, enable and reset. Okay, so the condition we noted is that the second bit toggles between value whenever the value of q is equal to 1. That is the least significant bit. Let me call this one q0. So whenever the value of q0 is equal to 1, we will be having a change in the second bit. So for that, we want j and k to be 1 when q is 1. We can do that simply by connecting it directly. Let me do this. I want to make it a little more neat. So let me do this by connecting it directly. So we can see that we have got a 2-bit counter here. Now to extend it to the third bit, we have, as we already noted, the condition is like uh, we have to toggle this flip flop whenever both the first and the second flip flop is having the value 1. And this isn't a hard thing to do. We can always use the AND gate. Let me make this a little small so that it seems neat with the circuit. So I brought in the AND gate, and I will connect both these queues. Here is the second queue, and here we are bringing up the first queue. So we want the JK, this flip flop, to toggle whenever both of these two, the least significant bit flip flop and the middle flip flop, turns 1. And that condition is only satisfied when the output of this AND gate is 1. And hence, we simply have to connect the J and K of this flip flop to this output from the AND gate that only gives 1 when both these flip flops are 1. First of all, let me enable this one. Enable preset and the reset. So we are almost done, but this only is the up counter. Now, for the down counter, we have to make a few changes. But it would be more convenient if we could have both the up and down counter in one circuit. And for that, let's create another input and call it up down input. So let's say that when this up down input is 1, this acts as an up counter, and when the up down input is 0, it acts as a down counter. Now, for this value 1, we want the circuit working as it is. So for the third bit, I do something very simple. I increase the number of inputs to 3 and connect this one directly here. So now this AND gate is enabled only when this up down input is 1. And for the second bit, what we are doing is like for up counting, the value of this middle bit toggles only when the value of the least significant bit is 1. And for down counter, the value of the middle bit toggles when the value of this least significant bit is 0. So either when the jk value should be 1, either when both this lsb and the up down value is 1, or for the down counter when the lsb is 0 and the up down input is 0. So you can there is this gate called XNOR gate which does exactly what we want, which in outputs the value 1 for the combination 0 0 and 1 1. For no other combination does it output the value 1. So here you can see for 0 0 we are getting 1, and for 1 1 we are getting 1. So we'll use this XNOR gate in our circuit. Let me bring this one here. Oh damn, it's too big. Let's make it a little small. Turn it southwards. Decrease the number of inputs. We only require 2 in this case. Connect it, connect, and connect. But now, for the third case, we have deactivated this gate, but we also need it to run when the up down value is 0 for the down counter. And we know that the condition for the down counter is like when both this middle bit and the least significant bit is 0, this most significant bit toggles, or basically when q1 and q0 are 0. Or you could also say when q1 complement and q0 complement are 1, we have to have this toggled when the up down value is 0. So to do that, it doesn't require too much of a work. We will again use an AND gate, basically the sum of product thing. Uh, we take the products uh, as we want in the true state. Oh my god, so much wiring. I will pass all of these into the 3 input AND gate. Let me copy it, turn it westward, put it here, bring the wire all the way from the up down input and get it inside this puny little AND gate, and then connect it. Oh god, there is already a wire here, so we want both the things to work at the same time. So we will use an OR gate. Note that only one AND gate will work at a time the way we are connecting this input. When it is 0, this AND gate will be activated, and when it is 1, the up down counter AND gate will be activated. Let's reduce the size of this humongous OR gate, or it is facing in the right direction. Let's make it narrow, and we again only need two inputs. Bring it here, bring it here, bring it neatly over here, connect it, connect it. So there you have it, a down counter. Not just a down counter, but also an up counter. Let me reset the values, turn this to 1, and enable all the flip-flops. So you have both the up counter counting from 6, 7, 0, 1, 2, 3, 4, 5. So we get it. This is the up counter, and for the down counter part, it counts back from its instantaneous state: 4, 3, 2, and 1. There you go. There is this circuit of JK flip flop. The circuit of a synchronous counter using JK flip flops.